Hello, hello, hello. How is everybody? I'm pretty sure today involves writing a parser. It certainly looks like that would be true. It certainly looks like that would be true, Nikki. Get rid of this VS Code instance. Let's go into day 16. Clear that out for a sec. Let's get a Chrome window in here. Oh no. That's gonna open everything I have open on my other computer. Oh no, we're good. You ever you click the wrong button on stream? And then you're like, I don't know what this is going to do. I don't know what windows this is going to pop up. Okay, 16. 16, 16. Let's actually move this to another window. If I can. There we go. Okay, so the day 16 is called Packet Decoder. Packet Decoder. Packet decoder is a packet decoder. Before we get into the explanation, we need to look at the input because otherwise the explanation isn't going to make a whole lot of sense. So this input here is a series of characters, basically. So like input.cars, we get an iterator over characters. All of these are from 0 through to F. So it's hexadecimal. So if you're unfamiliar with what hexadecimal means, it means that we have the numbers from 0 to 9, and we also have an additional, what is it, 7 digits. But since we don't have any more numbers, we have to go with A to F. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So it's base 16. And that's important because basically what this is we're going to take those hexadecimal numbers. We are going to convert those hexadecimal numbers to a binary representation. And this binary representation, yeah, we'll go over it later. And then basically what happens after that is there is a string of binary that is cut up into what they're calling headers and packets. So the binary string for the first 6 bits, the first 6 ones and zeros, that is the first 3 are the version number, the second 3 are the type ID, and then we have a series of packets. So this is exactly what NOM was designed for. There is actually in NOM, if you've been around for the other streams, we use NOM every single day. There is literally a bits package in NOM and some combinators to transform between bits and bytes for parsers. So you can do a tag of a specific representation of bits or take on a number of bits and that kind of thing. I don't think we're going to dig into this specifically today. Just because I think I've never used it before. And I think it's more understandable if I'm not parsing it as a binary format, but instead I am parsing it as a string of ones and zeros. I think the string of ones and zeros is going to be a conversation we can have on stream, and I can show you, and then we can have the conversation and I can show you. And then maybe later I do a binary representation of this. One thing that we can do to check here, right, So we've got some hexadecimal input and a whole bunch of like little rules that really, so the way that you would normally get like a spec to parse like this is from a spec. It's not from like English description like this. Like if you look at JSON, right? JSON has this thing on the right, which is very clearly defining the grammar in a specific way. In this case, it's called McKeeman form, but that's not really important. But it's like a JSON is elements, and values are an object array, string number, true, false, or null. So like normally you would get something resembling this if you were going to try to parse a spec. But this is a word problem, so Nom. I think of Nom doing all the work for us. Yeah, I mean, like, I really think that Nom is going to basically do most of what we need it to do here. I think really what I'm going to do is we can probably just get started here. I think I understand it. I think I understand it. I wish it was far clearer or the example was more step by step. Yes. I think we will get into why they explain it this way. Because it's a little bit like they're trying to describe each of the parsers as if you're writing a parser, and if you're not writing a parser or not used to writing parsers, then you don't have the context for that, and it's a little harder to understand. So let's get started with tests, right? We have a couple of tests here, a couple of inputs, which I'm happy about. Let's pull this whole thing in right here and code day 16, open a VS Code instance. And our VS Code instance is basically just going to be parsers today. So I'm going to get rid of most of this stuff because we don't need any of like the ND array stuff that we've been doing, etc. We don't need this insert. We don't need this like graph stuff. This is all going to return 0 for the moment. This is all going to return 0 for the moment. I assume we're going to be able to reuse the parser from part 1 to part 2 because what it says is basically like, don't worry about this input for now. So part 2 is probably going to be parse that input because, you know, what else would they be doing? Let's see. I think the part of it that I have the biggest challenge with is the subpacket stuff because they don't ever actually parse a subpacket. They don't show you what the result is, you mean? Yeah, I could easily see that. There's no like, here's a subpacket and here's the result in the description. This is definitely not going to be a separated list. And this is definitely not going to return an array 2. We're going to return a usize for the moment. It's not going to be a usize. I'm just kind of dealing with it for now. We can do to do here. And we can do to do here. We should start doing to dos instead of zeros. Okay. So let me, do I have the, I do have the copied stuff. Let's do this. Oh, I didn't even copy that, did I? That's what I get for trying to be sneaky. Comment this test out. We're going to take these. We are going to take this, 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 and this. Of course I messed that up when I did it. Why would I not have messed that up? There we go. And then we're going to do these, and I'm just going to paste these in for the moment. Actually, these are going to go in the beginning. I guess we're going to do process part 1 here because this is the whole thing. And then we're going to do like test function part 1 test. I'm going to call them like A, B, C, and D or something. Just because that's the easiest thing to do for me right now. And we don't really have any identifiers for them anyway. Assert equal with the macro. And then it tells me that I made a typo while I was typing all of these. Let's see. These are all A. So we'll change these quickly. B, C, D. And then, oh, right, because I left this stuff down here. Okay, so we have our test now. Except for the fact that I misnamed it. Let's just rename these to part 1. So we have a bunch of parsers. They're all process part 1, test day, whatever. And basically, why are those all yellow is my question. They all panic. Is Rust Analyzer being like, hey, I know these all panic? Is that what that yellow thing is? Focus errors. I don't think so. Let's restart Rust Analyzer and see what it does. Okay, so puzzle input. Puzzle input is going to be a series of hex codes, basically. And what we're going to get here is basically we need to go over all of the cars and turn them into binary, right? So we have 2 options. The first, I'll show the first one first. So cars gives us each character, right? And then we map over it and we get each character and we do character.2digit. I think it's 2-digit 16. Do we have our, I think that returns a result, and then we can collect back into a string. So this is like option 1, I think. We get a U32, radix 16, collect string. This is not the only thing we need to do. We need to also format this into binary. I think it's just B. We're going to debug. We're just going to call this binary. This is going to be let binary equals this. And what we end up with is this long string. I am going to .inspect car and just debug the car because I happen to know already what's happening here and I want to show it. So basically what we have here is a bunch of binary representations of each of the characters. So if we look at the test input, or not the test input, if we look at this chart, basically, right? This chart actually matches up with what the binary representation of each digit is. So 0 is actually going to be 0. If we ignore the leading zeros here, what we end up with is these numbers. So this character is 1. 1 is the number 1. So we would expect that to come back as 001, which means that here, where we are using format in Rust, and we're using the sort of binary representation in a string. So like we're taking the character that we have, we're taking the number, and we're showing that binary representation as a string, right? Using this formatter. And the thing that we need to do here, I think is like 04. So 04 will give us the padding character 0 up to 4 times. So in the table that we have over here, we have 4 characters. If the only thing we do is convert it into a binary representation, the leading zeros aren't going to be there, but we need them there for this format. So now we have 4 character binary representations of every character that we have in the hexadecimal input. So I'll just get rid of inspect here now. And that gives us quite a longer output for each of these inputs. And I think what we actually want to do here is I'm going to do this here instead, because in the future I want to kind of swap this out and see if we can apply bits to it. So I'm going to do puzzle input on the binary string. And okay, so one thing that's interesting here, if you're not as familiar with Rust, is that we collect it into a string, right? A capital S owned string, something that we can modify. That's what binary str is. I should not name this str. Binary as string. Usually I don't put the types at the end of stuff, but for clarity, I'm going to make sure that this is a string representation of the binary. So it's a string with 1s and 0s in it. It is not actually a binary like blob or U8 or something like that. So here, puzzle input we've defined as taking a string slice, right? Like string, capital S string, and string slice are not the same thing. str is, we'll call it like a static region of memory somewhere, right? It's a thing that can't change, basically. Whereas capital S string is an owned thing that we can modify and grow over time, just like we do with vex. So it's the same difference between like an array and a vec versus a string or a stir and a string. So what we need to do here is that capital S strings will dereference if we pass in a shared reference to string slice. So all we need to do here is, because capital S string implements deref and can deref to a string slice, we pass in a shared reference, and that's why this works. Okay, so now we have to start actually parsing the thing. Every packet begins with a standard header. The first 3 bits encode the packet version, and the next 3 bits encode the packet type ID. Okay, so let's start with that. I think we're going to end up using take. So let's go look at nom in the nom docs and see if take is the right thing. I'm going to use the complete versions of these for now. I don't need bits take because we're not actually working with bits. Let's not do streaming. Let's do complete. So take till, take while mn. What else do we have here? We need to start off with taking 3 of the bytes, basically. So there is, oh, you know what I haven't shown on stream, actually? The choose a combinator guide. So if you are working with NOM and you are working with it for the first time, this document here is called the choosing a combinator document. And the choosing a combinator document will walk you through, hey, what do you have and what do you want out of it? And give you the combinator or the parser that you should use to get that result. So let's take advantage of that to show you all what it looks like, because we haven't shown it off yet. In this case, we have a basic set of elements, right? The basics, the car, is it a thing? One of these, like all of the like, kind of the just combinators that match a specific kind of thing, right? And this takes 4. So this is probably what we want, because take 4 on a string of HELLO will give us HELL with the leftover input O. Remember that the return type is the rest of the input and then the thing it matched. So when you're looking at these examples, keep that in mind, because otherwise you'll start looking at the first part of it and think that that's the match. So it does look like take is what we want in this particular case. So we'll use that. So in this case, we'll do let input, what is it? The version, I think, is the thing. Take 3 input, and then let input type ID. Was it type ID? Take 3 input. So now we should have the version and the type ID for all of the puzzle input. And I think we're not debugging this out anymore, right? So I can run this on the right-hand side. And I didn't import it, so it breaks. We're going to use a complete version from bytes. These need to be U sizes. So one of the tricks we can pull here is if we do an underscore here and we specify a type, it'll make this type that, or make this number that type. So by default, they're like, I think I32 is the default number if you just write a number and there's no inference and there's no reason for it to be anything else. But we can make that like a U size. We can make that a number of other things if we want to. Let me pull this over here for a second. And then, there we go. So each of these, when we parse it, has a version of 110, version of 000. This is a version of 101. The type ID is 000. I believe the type ID 000 is just the first thing we have to deal with. Is there a difference between 3 U size and 3 underscore U size? I have never written 3 U size, but my guess is that these are readability, because you can put an underscore in any number. So yeah, there is 0 difference, just readability. The underscore is just a separator. So for example, in Rust, if I want to do like 3 billion, I can make it very clear that I'm doing like 9 zeros here. Which I actually encourage you to do if you have to deal with large numbers like that. The underscore separator is just a thing that gets removed, basically. Okay, so we've got a number of different results here. We need to parse these back in as binary. So what do I want to do here? Do I want to map into this? Let's not map into it for now. Let's do binary version and binary type ID, and we'll let version equals binary version from parse. What is the there's a digity thing here I can do, right? String slice rust radix. It's on the integer type, that's why. Radix. That's why I wasn't yeah, okay. This is going to be then, I don't know, let's make it like a U8, I think. U8 from stir radix. And then we need the string and the base, it's base 2. And then the same thing for the type ID, which needs to be binary type ID. And then if we debug that out, so what we're doing over here is we're taking the U8 type and we're doing from str radix, so from a string, basically, and we pass in the binary representation, which is like 101 or 110 or something like that. And then we say that we're in base 2, which is binary, zeros and ones. So we count with zeros and ones. And then that gives us an actual number here on the left. So OK4, OK2, OK5, that kind of thing. These have to succeed, so I'm going to unwrap them. And now on the left-hand side here, we can see version equals 4, type ID equals 2, that kind of thing. So we have the version and we have the packet ID, right? These two values are numbers. All numbers are encoded, whatever. The explanation here in English is not what I want to say. So binary sequence 100 represents the number 4. Yep, we already saw that. Packets with the ID 4 represent a literal value. Literal value packets encode a single binary number. To do this, so it sounds like we need a parser here. And it sounds like, so it sounds like we need a literal value parser, right? And it says the binary number is padded with leading zeros until its length is a multiple of 4 bits. So we're going to throw away any leading zeros. And then each group, after we throw away leading zeros, is prefixed by 1 bit, except for the last group, which is prefixed by a 0 bit. So we have groups of 5 bits that we need to parse. D2 FE28 becomes this. And I'm assuming there's no leading zeros in this example, just out of it being an example that doesn't represent the full input, right? So packet version and then type ID. So 110 is the packet version, 100 is the type ID. And then we immediately go into 5-bit groupings. So we need to parse these into hex, it looks like. Or maybe not, we'll find out. 1, 2, 3, 4, 5. So this goes all the way to 0, 0, 1, 0, 1. We throw away the prefix bit, as far as I can tell, and we only focus on the 4 additional bits. And then there are 3 zeros at the end due to the hexadecimal representation and should be ignored. And that's where I'm a little confused, because why do they say in the text that there's 0 prefixes on these things for padding, and then say that there's 0 postfix in the example? So we're going to have to figure out which one we actually need to deal with, or if we need to deal with both of them. Okay, so we have a literal value and an operator. Let's start with the literal values. Let's do a fn literal that takes a string slice and returns the I result that we're, at this point, very used to. And this is going to return... What is this going to return? This is going to return like a U8, I guess. And then we do let input bits, I suppose, equal, well, let's see. What we need to do, right, is check the next bit and determine what we do based on the next bit. So we only keep taking as long as that first bit is 1. Test prefix zeros. Example, postfix zeros. Yes, exactly. That is the frustrating thing about advent of code. And actually about academic papers in general. Take while. Right, we have a number of combinators that we can use for this. Let's see, take while might be what we want. Let's go back to choosing a combinator. Take while is alphabetic, so that will just test each of the characters. Take until whatever. Take until world. Take until is not what we want. We're going to need to use probably alt for our multiple version, like the literal versus the operator packets. First, take the continuous bit. Yes, I understand that that's what the instructions say. I am looking for a combinator that will let us parse bits until the first bit is 0. So preceded, terminated, pair, separated pair, tuple. I think terminated might be what we want. Let's open terminated, because then we could do literal values terminated in a literal value that starts with 0. So we basically have the literal value inside, right? And we have the kind of containing structure around it. We could also try to do many one or something like that, which could also work. Length count gets a number from the first parser and then applies a second parser that many times. That will be useful later, but it's not what we need yet. Recognize. Is recognize what we want? I don't think so. We could also write this with verify, although I want to avoid that. Success, fail, yada yada. Okay, so we're basically stuck with, I think, doing this manually. I mean, manually is a bit of an overstatement, but so let's try this with terminated first, because that seems to be interesting. So we have literal, right? And we actually have literal container 1. Input string slice. Right? And then we have literal container end. So these don't return what we want yet. Literal container 1 is going to let input container bit equals any car. Actually, we should do tag 1. That'll be a more understandable version of it. And then we'll do okay, and we'll do input, and we will do input what am I going to call this? We're just going to call this literal value equals literal on the input. And then this is going to be literal value. And we should probably parse in here. So this is going to turn into a number. So we're just going to take this from str-radix thing that we've been doing, and we're going to use this again for literal value. Oh, you know what? We actually don't need to. Whoops. My mistake. Literal value is already the U8 that we want it to be, because we used the literal parser to do it. So this is that, and then this is this, right? And this is tag 0. And then this is going to be terminated literal container 1, literal container end on the input. And we need to pull terminated in here from sequence. So now we should have, I don't think this parses the last one. So where we gets an object from the first parser, then matches an object from the second parser and discards it. That's actually not what we want. A, B, C, E, F, G. Okay, so actually, now that I think about it, this is not what we want. We want like take until. If we're going to do it this way. Because we don't want to get rid of... Oh, there's preceded, actually. Preceded is going to be super useful. Let's do this for a second. Let's go back over here, and where we have this tag 1, we are going to do preceded 1 literal. So we actually don't need literal containers here. And then this is going to be the same thing. We don't want terminated here. We want like take until or something. But preceded is going to take the first object, which is the 1, and then discard it if it matches, and then to get an object from the second parser, which is going to be our literal value. So take until feels like a better match. We could do like a many one, but really we're trying to go until we stop. So I'm trying to match the semantics here. It doesn't consume the pattern. So take until this thing. This is just arbitrary take. So we don't want take until actually. Take while. Returns the longest input slice, if any, that matches the predicate. We also have many 0 and fold many. So many 1 will fail at the 0. So we could do many 1 and then we could do the application. So if this is many 1 with the preceded tag literal on the input, then let input ending literal equals the preceded applied to the input. Wait, why did I didn't want to write this function? I want to import it. Did I spelled this wrong, didn't I? Pre? Yes, I did. Preceded. Preceded. Okay, so we've got many 1 that are preceded by a 1, so this will run until we get that ending, and then we get the last literal. So we don't need the extra combinators, custom combinators, because we already have the combinator that we need in the nom library. So the question I have right now is, how long is that? And I think the answer is going to come back as we need to parse that string out and then apply this other parser to it. So if we have this, first 3 bits, second 3 bits, then we look for 1, 2, 3, 4, 5. Then we look for 1, 2, 3, 4, 5. Then we look for 0, 1, 2, 3, 4, 5. And we need to keep track of how many of these we've parsed. Because what is that? 1, 2, 3 is 15. It needs to be divisible by 4, so we need to pad with 3 extra zeros. So this is going to return us something. This will return us input and the bits.length plus 1 and the actual value. So to do replace 0 there. We don't have a literal function anymore. Literal input. What did I do to the literal function? Did I delete the literal function that we just wrote? No. Why did I do that? Streamer brain, yo. It's real. Okay, so literal is let. We're gonna need this. We're gonna do let input value, not value, bits equals take for input. And then we're going to U8 from stir-radix bits. We're going to return OK, input. Value. So this is our literal. We do need take in here. Why is take complaining? We'll figure out why take is complaining in a second. Expected U8 found tuple. This is going to be a tuple now. It's actually going to be a U8 tuple. Whoa, that's the wrong spot to type in. This is going to be a U8 tuple. Actually, actually it's going to be a U size and a U8, right? Because length is a U size. So the trait 2U size is not implemented for I32. Because this needs to be U size. And there we go. So we have literals, literal. We have the header version and the header type ID. The literals function is going to return a number. So we're going to do match version, basically, right? When version is 4, then we literals the input. Right. And then this is an incomplete match. So what we're going to do is panic. Unhandled version. And this panic is going to be something else so that we recognize it. End of puzzle input. So when we have a version of 4, it's a version of 4, right? Not a type ID of 4. No, it's a type ID of 4. Okay. Type ID. Typed. And then we have the operator packets. So let's make sure that we're parsing this other stuff correctly. And then we need to take a skip value and the values here, right? So let input skipped equals take skip input. And then we just skip the padding, basically. Right? That's not the right thing to do. I did the wrong math. Bits.length plus 1 is the number that we have. This times 5, or not times 5, times 5 is the number of bits that we took. And then this mod is it mod 5 is the number that we want? Like if you're 15, right? Then you have 1 left over. It's mod 5. It's 5 minus mod 5? All of our tests failed as expected. Unhandled version, unhandled version. So C and D are unhandled versions. Unhandled version for B. Unhandled version for A. No, all of these are unhandled versions? Wait a second. So all of these are unhandled versions. We don't even get a test. What? Let's do this. Let's pull this one in. And let's get rid of these for now because they aren't serving us. Why did I click that button? Close. Get rid of these call stacks. We don't need call stacks. We don't need a debugger. We don't need to be running these tests like that. So these are the fuller tests. And instead, what I'm going to do, part 1 demo data, let's get rid of that one too, so that that's not running. And let's do test, and we will test, what are we, something, and we're going to assert eq that some number or something on the puzzle input, maybe for this unwrap. This is going to be a tuple, so we'll match against the result of that. The result of that, if we do puzzle input currently, is nothing, right? We get nothing back from puzzle input. So what we probably want here is some kind of struct, right? Header or version is going to be a U8. Type ID is going to be a U8. And then we have literals. Well, we have packets, which is going to be a vec of unit at the moment. I'm just going to call it unit because we're not going to return anything. This is going to be called a struct of what? Packet? We'll call this bits. Message retracted. I kind of wish that wasn't a feature. Okay, so the end of this is going to be a bits with a version, a type ID, and a vec, and a packets of vec. That's going to be a bits. Can't be formatted using debug because we didn't derive the bug. We need equality because we're using it in tests. No implementation for integer string slice bits. That is correct because in our test, we should have no more input and a bits of version something. I think it was 6. Type ID is 4. And packets of nothing. Expected result found struct bits. Where? 52? Yes, that is correct. That makes sense. Okay. Input bits. So we need to return the input and the bits for the return of the parser. Parse error invalid digit. Because we need it to be binary first. So let's do this. We're just going to copy this into a utility function, I think. Fn hex as binary string. Input is going to be a string slice. Output is going to be whatever this is. It's going to be a capital S string. And it's just going to be this. I'm going to take that and I'm going to put it here. And I'm also going to use it in our input parser. And a Rust analyzer can actually fix that reference for us, so that's great. So, puzzle input on this. Version 6, type ID 4, packets. The right-hand side has all of the input left for some reason. A version of 6, a type ID 4. So our packet parser, as it were, is failing. So let me fix this thing right here. String, and then we're going to pass in equals this input. Okay, so that works. And then are we debugging here? Skip 0, values 0. So literals is failing, basically, is the issue here. So we should be getting 101. We should be getting 111, which we are. And then 4, 5, 1, 2, 3, 4, 5. Why is that? That doesn't look like it's the right length. Oh, right, because this is the whole thing that we need to parse out of the other parser. So that's actually pretty perfect. Because we can write a test for the literal itself. And this is what I would do in general if I was writing we'll input fn test literals parser, right? This binary assert eq this binary should be, I forget what the thing that we have to make this is. What does this return? It returns bits. This returns a U size and a U8. So literals on this input input dot unwrap, because it does need to succeed, needs to be skip 3 U size 0 is what it is right now, right? Expected integer found string slice literals. What is the mismatch type? Expected tuple integer found string slice integer. Oh, yeah. Okay, yeah. The input here should be fully consumed. Well, no, it should be 0, 0, 0, right? So we need to skip 3, and we should have the value 0 that comes back. But it doesn't. So we get bits, the version 6, type ID 4 packets, right? And on the right-hand side, we have The full input. Oh wait, I need to ignore this other test for a second. Ignore. Okay, there we go. So we're supposed to skip 0, which is the wrong number, right? So that's our issue right now. So in literals, whatever I'm doing here, whatever strange math this is the wrong amount. Let input length equals input.len. Put len minus input.len. Let num parsed cars, right, equals this. So we can't really do this on a streaming parser, but, well, yeah. Can't really do this on a streaming parser, but it's fine. So we have the number of parsed characters, right? We've got the OK result. We've got the tuple with the input. We've got the thing that we are returning, which is num parsed cars 0, right? So what we end up with here is the value 15, which we need to bring up to 18, and we need to get that difference, basically. So when we do num parsed cars mod 5, we get 0 because it's equal to that. It needs to be 4. That was my mistake. And now we get 3. So this is the right thing. Num parsed cars mod 4. Because we need to know how many to add to get up to the next one. So this test should pass now, and now we have a parser that is successfully parsing. We can uncomment this test, which now should work, except for the fact that we're still left with all of the output. So there's something wrong with the full puzzle input. And it's because we aren't consuming the literals. Because we aren't returning from the match. The match is what we need to be returning from. This is the return value that we want here. So we're returning out of the match, not doing the match and then returning something else. Okay, so we've got our first packet parser. That'll give us the literals. It gives us what we expect here. It gives us this is bits. It consumes all of this input, which includes the padded input or the padded output. The prefix zeros is something we aren't handling. So that's a problem. We'll deal with that. We will deal with that later. Let me add a comment to that parser just so that I have a note. To do here doesn't deal with starting zeros. Okay, so we have the literals. The literals aren't coming back in the values yet. We should do that too. Where's literals? This is bits and ending literal, right? Bits, I believe, is going to come back as a literal. Literal is going to come back as a literal. Is that what we actually want? Is the question. This packet represents a literal value with a binary representation of this, which is 2021 in decimal. Okay, so my question is, should we be parsing the literal values here from stir radix, right? Or should we be doing that later? I think we should be doing this later. So this is not actually going to return the thing. This is going to return bits, which is a string slice. And literal itself is going to take not U8, because U8 is now going to be too small, right? Because we can have 4 digits. We're going to unwrap this because it returns a result and we need it to pass. The value is going to be a U32 from string radix with a binary of 2. And then this is going to be format bits. Bits and ending literal. So we're reconstructing the bits with the ending literal. And that should give us the value. We do need to pass in a string slice here. This does need to be, this is used after moved probably, right? No, it's not. What's the problem here? Menu, oh, it's a vec. I'm just going to collect it for now, because that is the easiest thing to do. And then we can always come back and turn this into something that's a little bit more efficient. We're going to take some ownership here. And then everything still passes, except for the fact that this needs to now be value, which is no longer a U8, it's a U32 because it's a bunch of literals. I guess this is a single literal, right? That does give us 2021, you see in our test over here on the left. So where is that test? That is the test literal parser. And this is 2021. So now our test should pass, and this is what we expect to get out of that. Wonderful. Wonderful. We still aren't returning this in the packets, which is whatever. We will need to do that. I think that we will build up a packet structure to handle that. Actually, let's do that now. Let's do struct literal enum packet. Let's do enum packet. Did we already have packet? Is packet? No, packet is not the thing that we're doing. Enum packet. That's going to be literal U32. And this is going to return a packet. Nope, that's not going to return a packet. This is going to return a packet. And this packet is going to be packet literal value. And I'm going to correctly identify how many ending parentheses I'm supposed to have. Where is the take from nom imported? There are many in the description. The take from nom is right here. So it's bytes complete take. And we're doing bytes complete take because we're not actually operating on a binary representation, so we don't need to take bits right now. We're still operating on a string of ones and zeros, which is not actually like binary. We're kind of faking binary right now. Okay, let me move this back over to the left. Give me a little bit more space. Now we need to update this. This is going to be packet literal 2021. And this is test literal packet. Let's call this packet literal parser. And packet doesn't implement debug or equals or anything else. So we still need to do those. Derive, debug, eq, partial eq. And we have to do eq and partial eq because of the tests again. We have to do debug because we print this out in random places. Okay, so all of our tests pass. We're starting to have a representation of the packets. And then we have the literal values, which is great. Every other type of packet, other than the literal, any packet with a type ID other than 4, represents an operator that performs some calculation on one or more sub-packets contained within. It performs operations on its own packets. Ugh. Right now, the specific operations aren't important, focused on parsing the hierarchy of sub-packets. An operator packet contains one or more packets. So it's a recursive packet. To indicate which subsequent binary data represents its sub-packets, an operator packet can make use of one of two modes indicated by the bit immediately after the packet header. This is called the length type ID. If the length type ID is 0, then the next 15 bits are a number that represents the total length in bits of the sub-packets contained by the packet. If the length type ID is 1, then the next 11 bits are a number that represents the number of sub-packets immediately contained by this packet. So we've got to check for 0 and 1 and parse 15 or 11 bits, and then we have to do more. Finally, after the length type ID bit and the 15 or 11 bit field, the sub-packets appear. For example, here's an operator packet with a length type ID 0 that contains two sub-packets. So packet version 1, type ID 6, 0, which means we take 11 bits. Guess that's 11 bits. Oh, no, 0 means 15 bit, sorry. Which means that this entire thing, 27, yes. So the length of 27 is the rest of the packets. The 11 bits labeled A contain the first sub-packet, a literal value representing the number 10. The 16 bits labeled B contain the second sub-packet, a literal value representing the number 20, which I assume once we construct the first packet with the 0s and the 1s, that's how we do this. Or something. So an operator packet can contain a literal, or it can contain some random thing. All right, let's start with let's start by adding operator here, right? The operator packet is something. I don't think that we are handling really what it is yet. The length type ID. So recursion, right? Yes, basically. If the length type ID is 0, then the next 15 bits are a number that represents the total length in bits of the sub-packets. So this is going to be take 15. If 0, take 15. If 1, take 11. So we are going to have two new parsers, I guess. Let's start with operator. String slice. I result as usual. Wrong line. And then this is going to return a packet. The packet is going to be an operator packet, so we're going to have a return value of something like input packet operator. And then we do one bit, right? Input, what do they call this in the thing? Length type ID equals take one input match length type ID 0 do something, 1 do something, anything else panic invalid length type ID. And this is going to be the return value for both of these things, but we're going to do here and we're going to do here. How are you supposed to know how many subpackets are contained when you have a length of type 0? It just tells you how long the total digits of the subpackets are. I assume we have to reapply the packet parser. Expected string found integer, that is this and this. So 0 and 1. And then we have required by this bond. This is a use size. You'd think that this could just be inferred. That was my confusion too. 15 for 0. So 0 is let input length in bits. Equals take 15 inputs. And then we need to let bits equal take length in bits input. And this needs to be the little fancy from stir radix thing that we've been doing. Takes the use size. Okay, so this is what we do for 0. We take 15, we get the length in bits. I think we parse this as a number, right? And then if the ID is 1, the next 11 bits are a number, also a number, that represents the number of subpackets immediately contained by this packet. So for 1, this is going to be 11, and this is going to be not length in bits, but number of subpackets. Finally, the subpackets appear. For example, here's an operator of packet with a length type ID 0 that contains 2 subpackets. That's the 15-bit version, right? So the 15-bit version isn't the one that we care about because we already know. I think this is just going to be like we're writing a packet parser, and this needs to go back and just reapply the packet parser. So I think what's going to end up happening here is that this is going to turn into this thing, and we're gonna recall it. Another example, here's the operator packet, the hex string, whatever, with a length type ID 1 that contains 3 subpackets. 3 bits for the version and the ID. The bit labeled I is the length type ID, which indicates that the length is an 11-bit number. We grab the 11 bits, that returns the length of the subpackets 3, and then we take the same number over and over. You see that? So we determine if we have the number of packets, we use the same number to get the length of each packet. So let packets equals many 1, take 11 use size. Let's do, okay, one thing I want to do is from bits 11 use size, right? This is something that I want. I need more water, so I'm gonna grab some water, and I will be right back, and I will answer your question when I get back, Derek.
Okay, so the question, how do we know that if we get the number of packets, they'll be the same length? How do we know? We don't. We're basing that on the fact that it is the only length mentioned in relation to the packets. So we've got two sub-packet types here, right? Like we've got an operator packet, and that contains one or more packets. To indicate which subsequent binary data represents its subpackets, an operator packet can use one of two modes. So we've got two modes for this operator packet. Indicated by the bit immediately after the packet header, this is called the length type ID. If the length type ID is 0, then we take 15 bits, and that represents the total length in bits. So we need to parse the next total length, which is after the packets, right? And that is our subpackets. We're going to have to figure out what those are at some point. If the length type ID is 1, then the next 11 bits are a number that represents the number of subpackets immediately contained by this packet. And the only number that comes up when we talk about what the length of those packets is in the second example of the subpacket, which is the one mode subpacket, the 11 bits labeled L, the 11 bits, the 11 bits, the 11 bits. So it's only 11. Well, it could be any number, right? So the way that I'm coding this, since packets contain their own length, essentially, is it possible that this is just a coincidence that they're all length 11? We haven't covered parsing the subpackets yet. So we'll look into that later, basically, is the thing here. So basically, Derek, we haven't gotten to the point at which we have written enough code to need to know this information. So we don't have the context from what we're parsing, which is necessary context for reading this problem. Because we don't know what the structure of our parser looks like yet, right? Because we've got here, what, like operator, whatever, and operator, whatever. I guess these are both operator packets, so it's not really a big deal. Because operator has its own packets, right? And this is a vec of something. We don't know what this is a vec of yet. I think you took my statement for being a definitive explanation of what the number actually will be. And what I'm actually doing is reading off this example and converting that into something that runs on this example. And then what I'm going to do is take this and apply it to the other examples that we have and see what happens, right? I'm not declaring that these are always going to be 11 bits. What I'm saying is that these are 11 bits in this example. We are going to code against this specific example, and then we're going to expand to other test cases. And when we expand to other test cases, what happens is that we will filter out whether these are actually going to all be 11 or if they're going to be some other number. That's what I mean by the implementation informs the other half of the problem explanation, right? This is not a complete explanation of the packet format. The packet format is this explanation plus the attempt to construct it, which will inform us from the test data that we have what can actually happen. All right, where was I? Number of subpackets. This is take usize. Right, I was going to do num from bits. Yeah, I don't like that for a well-formatted problem, in my opinion, at least for something like advent of code when there's room for the problem to be well-defined. Yeah, I will say that if you're implementing something like an algorithm from a paper or something like that, this is what you'll run into. You'll run into the paper saying one thing and the implementation requiring that you do something else or requiring that you gather additional data. So really, and like a really common example, I guess, is Paxos got really popular at one point, right? And the paper that defines how Paxos operates doesn't actually give you enough information to determine how the implementation should behave in practice. So there's like implementations of Paxos that do different things, but they're still the Paxos algorithm, right? So when it comes to implementing an algorithm from a paper or something like that, this is exactly the problem, right? The problem is that there is something that is a spec that somebody who understands the problem has written, but that doesn't give you enough information to actually do a reliable implementation. You still have to build up the test cases. You still have to do the benchmarks. You still have to figure out, okay, if we build it like this, is it going to break in these other ways? I totally agree that advent of code could choose to not do this. They could choose to define these problems in such a way that gives you very clearly all of the information that you need in a readable format. For whatever reason, they have chosen to not do that year after year after year. So it's unlikely, very, very unlikely that that is going to change. What am I doing here? I'm blanking. Let's not write num from bits right now. We can do that later. Many one take 11 usize. Then we need to do this. I think we can just map this. The map res. It's so weird that take won't infer the digit to be usize. So take is an input, output, count, and E, right? Where the count is a generic C. C implements 2 usize. So the issue here is this 2 usize is probably, yeah. So the 2 usize is a custom trait inside of nom. The issue here is that we specify a count and a thing that can go 2 usize, and the number that we're specifying doesn't have an implementation for 2 usize for whatever reason. So all it is a mechanical, like there was a choice made, and that's why we have to specify. Okay, so packets, take 11 usize. I think we're just going to leave that for the moment. And we're going to do, okay, input, packet operator, packets. And this is of string slices or something, right? Expected vac found tuple. Packets is a tuple? Why is packets a tuple? What have I done? Because it returns us the input for each of them. So maybe we do want to do this. Do packets from length. FN packets from length. Input. String slice. Something. This. I guess this isn't the same. Right, like if this is the same thing, then it doesn't really help us, actually. Found opaque type. Interesting, interesting. So that, I think, is going to be the issue there. Oh, input. That's why I needed to apply input to it. So this is still a tuple. Oh, right, because you know what the problem was? I've got streamer brain. Input packets. There we go. And then packets is that. And this doesn't need to be up here. And the type needs to change to a vec of string slices for the moment. Which, instead of doing this, I'm just going to clone it basically for now. Packets.iter into iter .collect vec string. I'm doing it like this because I'm going to change it later, and I don't want to write lifetimes into this if I don't have to write lifetimes into this before I change it. What did I do wrong here? Packets is a vec of string slices. If we iterate over it with into iter, What am I... What did I write wrong here? I messed something up, and I don't see the typo that I made. A value of type vec of strings cannot be built from an iterator over elements of string slice. I can easily fix this. I just don't know what I wrote to make that happen. I can map string to string. I shouldn't have to. I'm just going to ignore it for now, assume I made a typo, and come back to it later, because this code actually is going to get thrown away, so it actually doesn't matter. Num packets. Actually, this take isn't what we need. Why did I do that? Many take 11, right? Num packets. This isn't many take 11. This is take 3. Take while, take till, take tag. So is this num? Where's the modules? Branch, bytes, character, combinator, sequence, I think is what we need. Pair, preceded, separated pair, terminated, tuple. Where's many come from? Multi. Multi is really what I wanted, I think. So we're going to use fold many mn, I think. The other option is many mn. I think many mn. So many mn. I don't think that there is a many m, right? Yeah, many mn. So this is going to be num packets, num packets. We have to get exactly 3. And we're just going to take usize. There's a type error here. It's going to be expected usize found tuple because this is input num packets. This is one of the places where like nom supreme can come in handy, because especially when we're writing these parsers in for advent of code, it's a lot of little parsers. So expected usize, we still need this. So let's grab this and pull it out. Number of subpackets is 11. So I need to figure out what I'm going to call these. This is number of subpackets. This is the what? Parsed number of subpackets. And then here we get to do let packets equals this, right? Wait, let me read this again. I got distracted explaining something else and I lost my train of thought. Okay, so ID1 is 11. 11-bit number representing the number of subpackets. So we need that. This is going to be num subpackets. And this is parsed number of subpackets. What am I doing right here? What even is that? Num subpackets here is what we want. And then we do this. So we take the 11, we parse it into a number. We use that number to grab the next 11 subpackets. And this is the place for concern, right? So to do, what is this number actually? And I think that what's going to happen is that we're going to recursively parse subpackets or something. So all of our tests currently pass. We haven't set up the test for these yet. So we need to set this up. Right? And we'll test both of these, I suppose. We'll start with the one because that's the one we were working on. But we need to test both of them. So this goes here, and this is test. Actually, this isn't puzzle input. This is test subpacket 1 parser. Operator 1 parser. Which will give us, we need this, we need to bring this in. Hex as binary. So we don't want to apply puzzle input, we want to apply whatever we called this thing, operator. And this is going to be a packet. Packet operator. The operator packet is going to have a set of packets. The set of packets is not going to be 0, but we're going to run it and make sure that we get a test failure and not a panic. EOF. At 170. So that's here. So we ran out of input for our first parser. So let's go back to operator. Operator, we take the bit, right? If the bit is 1, we take 11. Then we unwrap. Then we take num subpackets. 1, 2, 3, right? So let's do this. Let's debug. Num subpackets. $17.60. That is incorrect. We don't take an 11, do we? So, example here. 3 bits, 3 bits. Ah, this is a full thing. That's why. So let's take off the, what did we choose to do for the other test? We chose to just call literals. So let's take the binary encoded version and not do the hex stuff, because we're not doing the whole thing, so that we know exactly what we get. And then we chop 1, 2, 3, 1, 2, 3. We chop 6 off the front, and that should be okay. So we get 3 packets. These are the packets. Question is, are these the right packets? The 11 bits labeled A. So let's see if this matches the first one. It does. So these are the packets. We're parsing the right packets out. And then I guess we have to skip some at the end or something like that. I don't know why these zeros are here. We might have to do the same skip thing we did before, because I think we're getting back 5 zeros on the right. Yeah, 5 zeros. So we do need to probably do the skip. Because we need to do the skip, that makes me think that, where is this? There's something that says 4 in here. Broken into groups of 4 bits. So this is only saying that it's literal values, right? And this doesn't start with a 1. So if we parse this sub packet as a, what's the, if we parse the type ID out of this, do we get something interesting? Because this is supposed to be 1, 2, and 3, right? Yeah, 1, 2, and 3. So that's 1, that's 2, and that's 3, which means that the literals here, right, is not what we want. But we do need the container. We need a container around these of some kind. So I wonder if it's the full container, if it's a version and a type ID, in which case we would chop off 1, 2, 3, right? 0, 1, 0, and 1, 0, 0. So if we do 0, 1, 0 is 2, and 1, 0, 0 is 4. So that's 4, which means that we parse a literal, and because it starts with a 0, this is the last literal. So the interesting thing in that is that we can have a literal. Where's our literal? If I can find where we wrote the code, we can have a literal here that is many 0 of that. This doesn't have to be, this doesn't have to pass, basically. We don't have to have this first one. We have to have the second one. We don't have to have the first one. So here we actually want match bits, right? I think this comes back as an empty string. Match bits length, or an empty vec, sorry. Match bits length. 0 goes somewhere and does basically ending literal. And then 1, or anything else actually, goes here and does that. What is the problem there? expected a struct string found string slice. Yes, in the test. Yes, aware of that. Temporary, which is freed while still in use. Damn it. Curse you. Which makes sense. It's fine. It's exactly it's exactly fixable. So I don't want to save that VS Code as a different thing. Thank you. I need to disable that. Let's pull this out because it's getting a little confusing. Stir to parse. Let stir to parse equals this, right? And the type on this is a string slice because the ending literal is a string slice, but this is going to have to be a string. So this has to be dot to string to match the types of the match. Thus, this has to be a reference to that string. So because we are constructing a string in one of these match branches, we have to return a capital S owned string from both branches because the type that comes back from this match expression from both branches has to be the same type. And then we're okay. And then our test down here still doesn't do the thing, but that's okay because we expected that. And these are going to get changed into something else in a second anyway. So the question then is, why doesn't end s cast string to string slice? It does. So you're talking about the, like, why didn't I do that from the other match branch? Because we construct the string right here, right? We format these bits into iter collect string, which I guess now that I think about it, we can just keep doing that because bits is going to be an empty string. But in any case, the thing we do right here with format constructs a capital S string. So now inside of this block, we've constructed a new capital S string. When this block ends, that capital S string gets dropped and goes out of scope, right? Unless we return it, in which case it gets moved into str to parse. So if I do this, we will get a temporary is dropped while still in use issue, I believe. Except for the fact that I two-stringed this. So borrowed value does not live long enough, right? That's because, and like, just to make it clear with the error message, right? Like on line 81, we do a reference to an S, which is a capital S string. And then at the end of the block on line 82, the very next block, like the very next ending brace, that capital S string is dropped. So we can't give somebody like our book to borrow and then burn the book, right? Like we can't give somebody our red ball and then pop it, right? They don't have the red ball anymore. They have like a flat ball. So that's what's happening here. When we return an owned type as a reference from a place where it's going to get dropped out, that's basically like saying, hey, here's a red ball. It's really great. You should totally play with it. And then like sneaking into their garage later and popping it. But we can actually just use this whole thing, I think, because I don't know where my brain was, but bits into iter on an empty vec collected into a string will be an empty string. So we'll just get the ending literal. So what we need to do here is we have another bits, basically. So we need to take this puzzle input, and where is the place that we're doing this? The puzzle input will be here. All right, so num subpackets, and we're parsing puzzle input. So this is going to be bits, actually. Expected string found bits. So where's operator? Operator packets bits. And then I think this is our test failing. And then we need to figure out what these are supposed to be. These are all literals. Why is this not formatting is my real question. So I'm just going to do bits with garbage values for a second. I'm going to take this and I'm going to go bits, bits, bits. And I'm doing this because what I want is the information from the failing test. Unhandled version. Okay, so what happens here is that we are recursively going back, right? And we are saying, hey, we have packets here. The packets are their own full packet. We need to parse the version number out. We need to parse the type ID out. And then we need to keep going. My guess in the end is that bits and packet become the same thing. I'm keeping them separate for a moment just because so people can follow, basically. So we hit this unhandled version for num subpackets, type ID. So does this not come back as literals for each of these then? Is that a problem? Type ID 0. Do we get a type ID 0? Are we supposed to get a type ID 0? Is my question. I wish this page was at least had headers or something. That would be great. If I'm going to have to flip back and forth between all these paragraphs, I would love if it had headers. Yes, part 2. I don't know what you mean by yes, part 2, Commander. Okay, so we have the 11 bits labeled A, right? So let me pull this whole thing over. Part 2 is not, we don't care about part 2 yet. So right now, what I think is that we have a bug in our parsing because I don't think we should be getting type 0 yet, is what I meant by that. Can I open just like another VS Code or something? I'll just put it into the menu bar. I don't know. Let's do gist. So we're at this for A's, this for B's, and this for C's. And then we have 5 zeros left over. Okay, so 0, 1, 0 is 2. 1, 0, 0 is 4. And we should be parsing 4 for all of these type IDs then. So what we have here feels like a problem, right? While we're here, 0, 1, 0, 2, 1, 0, 0 is 4, and 0, 0, 1 is 1. So 2, 4, 1. This is version 2. This is version 4. And this is version 1. Test operator 1 parser. So this is the thing that's failing. Let us, where did we debug for the type ID? Input type ID. Let's debug the puzzle input actually. Debug input. So now when we look at this, we get num subpackets 3. Does this look like on 91 the right thing? So let's pull these back. Yes, that is the right thing to try to parse, right? So we should get here 2 and 4. That's input. Let's do version type ID input. So we get 2, 4. And then we're left with the input here, which feels like it might be off. 1, 2, 3, 4, 5, 6. Nope, that lines up. And then we should parse these 5 off. So 0, 0, 0, 0, 1 should get parsed off. And when we go back into the puzzle input, it doesn't look like that has happened. It looks like we've only taken 3 characters off. So my guess is that the problem is right here in num parsed cars. So let's take these 3 values that we're supposed to have here, right? And let's pull them in and let's throw them into a second test just to make sure that we can parse these values. Where is our literal parser? Literal parser is here. I believe that this is telling us we need to skip. Are we not actually executing the skip? If we're not actually executing the skip, that is the problem, right? Match type ID skip. So I think we are executing the skip here because we're running that. So if we're executing the skip, then this could be a thing. right? So we get this, we get 2, we get 4, which are correct. Then we have 0, 0, 0, 0, 1. That is not actually a skip, now that I'm thinking about it. So we don't have a skip. We just need to parse that value, which we are not doing correctly. And we're passing back invalid input into the next iteration. So I want to do what I was saying I was going to do before I started debugging stuff. I'm going to write tests for the packet literal parser that use these 3 values. 1, 2, 3. And this is going to be this V. So now we've got these 3. I'm just going to start calling these like A, B, C. Okay. So these should have nothing left over, all of them, except for the last one, but we skipped that. 2, 3, 4, 5, 6, right? So this should parse as a literal. 1, 2, 3, 4, 5, 6. This should parse as a literal. 1, 2, 3, 4, 5, 6. This should parse as a literal. And they all fail. So that's our problem. We aren't parsing this correctly. So let me, for the moment, ignore this one. Is the to-do here doesn't start with the padding piece? No. This is not padding, though. This is not padding. This is the last set of bits in a literal. So it's this parser right here. It's the ending literal. It's preceded by a 0, and it's the literal. Right? And the literal is take 4. So it should be all 5 of those bits. For whatever reason, it is not. And that is returning us invalid data into the next one. So cars here, wherever cars is, right? Did I say cars? Num parsed cars. Subpackets, literal. It looks like we are getting literals. 1, 2, 3. So those literals parse correctly. That's not the problem. Where's our literals? This is 1. This is 2. This is 3. This is 0. This is 0. And this is 0, right? Well, that's not true. I think we need to ignore the skip. Because these will come back as 3 for the skips. Right? 0, 1. Oh, right. These are... Yeah. So for B, the left side, which is the one that we set up, should skip 1? Why should it skip 1? I think the unspoken rule here is that they get packed together. And we are actually executing the skip, maybe. Because I think this pulls 5 out, right? Five mod 4 is 1. 1 is not the right number. Right? The literal parser is failing now. So something to do with our skips and our offsets is the problem. (15 mod 4 is 3 because of 12. But we need to pad upwards, right? 12, 13, 14, 15. So we should only have to pad that with 1. I have now confused myself on how we're just supposed to do the skip. Wait, the integrated terminal has a search command? This is not the integrated terminal for VS Code, Nikki. Sorry to tell you. This is Alacrity. Alacrity? Whatever. Okay, so what is the actual thing that should happen here? The literal for 0, 0, 0, 0, 1 should parse this just fine, right? And then where do we put the skip logic? Because the skip logic doesn't need to happen until the end, if I'm reading this correctly, right? Because if we do 101, 111, wait, that's not the right one to look at. I wish these were better organized on this page. This is the 11 bits one. Okay, so we're 011 or 010, 100, which is 4, and then 1, 2, 3, 4, 5, right? So we are at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's 11 bits, 3 of which are the header, 3 of which are the second part of the header, and 5 of which are the last piece, but then they're packed together with no spacing. So we can't skip in the bits location that we're skipping currently. I think the skips might be correct, but we can't skip there. We need to accumulate these skips somehow, because this adds up to the right number of skips. So how do we do that? That's the question. We are doing puzzle input for bits here. We are skipping here. But we really need to skip at the end of the batch, not here. So only the exterior skips. Where is that on the exterior? Maybe we pass in a value here. It would be awkward a little bit. Right? It would be really weird to do like an init is outer packet, right? Like this would be really weird. We do need to call this function again. So like, if is outer packet, skip, else, do nothing. And then if we do that, and we recall all of our puzzle inputs correctly, this feels weird. I'm just testing it. This should be opaque to a user. So for puzzle input, if we were going to do this, I would write a second function that didn't do this. An outer packet. And then when we call puzzle input up here, we need to find a way to pass in that bool value. Which I don't like. I don't like that we have to pass this around. I think it will be okay to ignore the rest of the binary. I don't know what you mean by that. If no parser fits, skip. We're parsing arbitrary bit lengths, though. The issue here is that when we are in a sub packet, we don't skip, and we are in an outer packet, we do skip. So when it's in a container, basically, right? What does the skip do? The skip pads. So if we look back at the value here, right? There's a header, there's a version, a type ID, the first number, right? The second packet number, the third literal number, and then the literal is padded with zeros, right? But it's not actually the literal that's padded with zeros. It's the entire, like, each group is prefixed by 1 bit, except the last group, which is prefixed by a 0 bit. These groups of 5 bits immediately follow the packet header. Is it calling postfix zeros leading zeros? Is that what it's actually doing? If the input length less than 11, then there cannot be any more packets in it. That is not true. That's not guaranteed to be true anyway. I'm not going to do that. The 3 unlabeled 0 bits at the end are extra due to the hexadecimal representation and should be ignored. But we should know what that padding is, right? Like, we should know whether we should be throwing this away or not. We shouldn't just throw stuff away randomly. So we get version, type ID, num1, num2, num3. And then I guess this is just the end of the entire thing, right? So I guess whatever we're left with then it's always going to be on the end of the entire bits, like the outer bits. So we just deal with that at some point, and we don't pass this thing in. Puzzle input is outer packet. We're going to remove this. We're not going to do this is outer packet thing because we're not going to skip here. We are going to deal with the skipping later. We're just gonna let this parser go, basically. We're not even gonna worry about the skip values at the moment. I'm gonna keep them around, I think. But we are not gonna use them. So if we cargo test right now, where are we at? We are at, these have extra values of 1, which is correct. We will update these. Our tests are passing at the moment. This... Yo, just chimed in. Is this part 1 or part 2 already? This is part 1. We're reaching the end of part 1, but we wrote a whole parser for this. So we're about to hit part 2. Bits version 6 type ID 4 packets. Version 6 type ID 4 packets. This has these left over, which is fine. Where is this test? This test is here. This will have 0, 0, 0, which we get to just ignore. As long as the ends are all zeros, then we can just ignore them. So let's get this operator parser back. We aren't doing the skips anymore. So we end up with the 5 zeros at the end. After 11 hours, I just passed part 1 myself in Python. Nice. I think we've been going for 2 hours, 2.5 hours, depending. Streaming is a little time bendy, so... So this is passing now because we're not doing that weird padding thing. Are we ignoring any of these other ones? No, we are not. So we're good. And then does that mean that these tests that we set up earlier will now pass? That is the big question. Nope, none of them pass. When am I? Yeah, exactly. Exactly, actually. Actually, exactly. Okay, I'm good. Okay, what was I thinking? So we did the ones, we didn't do the zeros. We still need to do the zeros, which are going to be the same thing. So now that we know that it's the same thing, we can just go back up here. And we don't really care about the lengths. Where's our operator parser? Operator parser here. So what we're going to do is sub packets. We're just going to run puzzle input here. And we are going to do puzzle input on this bits. Bits. Packets, we're going to call this. Equal many1 puzzle input. Syntax error because I just jammed that right in the middle of another function call. Like, yeah. That's how you do it, right? So now we're returning our operator with the packets. Did we set up these tests correctly? No, these are the full tests. These are the like actual run this and get a result tests. Unhandled version, that's not good. So type ID 4, and this is actually 401. So the parser that we wrote up here for operator, type ID 4. Did we get type IDs for these? Is that what it was? Packets with type ID 4 represent a literal value. This description is so wordy. I have trouble just finding where I want to be inside of this document. Okay, that's 3. We have to add up all the version numbers at the end, which is fine. Because we have to do bits again, 4 is a literal value. I think all of the examples here we have are 4s. Every other packet is an operator. I think every packet is actually an operator. Well, yeah. Words. Single packet of the outermost layer. Like, this is just going to be packet at the end of this, I'm pretty sure. Hexadecimal rep, 0 bits. So type ID. Let's find for type ID, because I can't find where in this document I'm supposed to be looking. Finally, after length, hex string with length type ID 0 contains 2 subpackets. The packet type ID 6, which means the packet is an operator. The bit labeled I is the length. Okay, so 6 means we have to do operator here. So 6 is operator. You think it's just this? I think that you are mostly correct, except we have not identified other like type IDs. The other problem is that we aren't returning bits here. So I think this is either packet bits or packet operator, which means that this is not here. This is here. And this is a packet. So we end up with this like recursive thing here, and this is a packet. And this is a packet, bits. And this operator what do we return from this operator here? This is, if this is a packet and that is that, then this is supposed to be expected enum result found tuple. We can just do operator input. We do need to change our test because now those are packet bits and not just bits. Packet bits. Ta-da. So all of these tests are going to fail currently. So let's just do one of them so that we only get one failing test. Let's get rid of all of these debug statements. Cool. So now we're getting our failing test. And the result of all of this, that's puzzle input. So what we get back is a packet. Let's just debug packet here. Take a look at it before we go into everything. Packets, operator, bits, version 6, type ID 4. So for A, whatever A was, this one. Operator packet version 4, which contains an operator packet version 1, which contains an operator packet version 5, which contains a literal value version 6. This packet has a value. We're not keeping the versions for the operators, are we? So we need to do what's here? We need to make sure that those return as bits with an operator in them. Scrolling around all of this code. This is packet with just a single operator, right? And then these come down too. So we always get a bits from this. This needs to parse. So all the way down here, we'll wrap this in a block. We do let packets equals this. Then we do packets, bits, packets, and this is just packets, right? Except that that type won't be correct. This needs to be okay. Input packet bits. And that will come from this, which is input. And packet is a single packet, I think. But we're just going to do this for a second. What am I typoing here? There's a syntax error. Version, type ID, packets. Are these types not correct? Packet is a single packet, which means packet. Version, type ID. Okay, with a tuple. Expected result found unit because I messed something up. There we go. I was missing a curly brace. Okay, packet there. Expected unit found packet. So this is the change here. So this is just a vec of packet. Which means that what we get here is now 4, 2, so what, 2, 2, 2, 4? That doesn't sound right. Oh no, the version's 4, 1, 5, 6. And this is 4, 1, 5, 6. That's correct. This structure that we've used here is awkward. I think that what I'm going to do is this. Get rid of bits entirely and just call this operator. And this will return a vec of packets instead. Which brings us to bits here. Which means that this operator has to have a version and a type. Bits are not a thing anymore, so we do operator here. At 202, expected tuple stir packet found stir vec packet. Packet operator version 2 type ID packets vec. Did I mess up? Let's get rid of all of these interior packets for a second. This is a vec of packets on the outside. That's the problem. So this is not that. This is a vec of packets. Flat out. Because we're just testing the vec packet, expected enum packet. So this is Rust basically guiding us through this little refactor that I'm doing. And the refactor that I'm doing is basically to remove an extra level of indirection in the struct that we have. So we still get 4, 1, 5, 6, but you'll see that we only have the operator packets now. We don't have bits and operators. So we're not going to need to flip-flop between them when we do the traversal here. Okay, A still panics and not yet implemented. Because what am I testing with A? The whole thing? Process part 1. Process part 1 on 135. Which is correct. So we have our packet. And basically what we need to do here is fold the packet. So packet dot if let packet operator packets equals packet here. And what did I do here? This is version type ID packets. And this is not a tuple, this is a struct. So we're destructuring the struct off of this. So I think what we do here is packet no longer looks like a word. Yeah, I hear you. I definitely hear you there. We are going to do are we going to do a fold? We have to do a traversal of this, basically. So basically it's going to be like packets.iter .fold with an initial value of 0 probably, and then the accumulator and the item. Fold is giving me a problem probably because I misdefined the this function takes 2 arguments, but 1 was supplied. Supplied 1 argument. I feel like I supplied, oh, is it this? And thus these are not actually a tuple. This is Rust saving me with its types again. So now we have a packet, and we basically need to do the exact same thing, right? You sure it's spelled like that? Like packets? So let's start with version, I suppose, right? And then what? We have like a process packet function that takes a packet. And we do this. And we process packet. And it's just a continuous fold here. This is needs to be fn. This is going to return a u size. Expected enum packet found a reference to a packet. We can deal with references. References are perfectly fine for us. Expected u size found u8. We're going to cast the value as a u size. Process packet, send it to the packet processing plant, and we just return that value, which currently is a u size, so that's what I'm going to do. And hopefully A passes. A passes now. So we traversed over that successfully. Let me check the other 2 before I explain what we did. Other 3, sorry. C and D failed. Okay, so we've got something to work on here, at least. We could potentially impl here something, Derek. Okay, so this is assertion failed, left 3, right 40. Let's debug packet and see what happened. So all of these versions are 0. This one's a 6. Type ID 4 is not getting a literal here. The video lag thing, don't worry about it. Yeah. Okay, cool. So let's take a look at C. This is C. Same structure as the previous example, but the outermost packet uses a different length type ID. This packet has a version sum of 23. Did I set these up correctly? 16 to 23. It's important to make sure that your tests are using the right values, because if they are not, you are in trouble. Okay, we're still getting 40, so we're still doing something wrong. Has the same structure as the previous example, but the outermost packet uses a different length type ID. Did I hard code something in here? Is a question that I have. You know what I'm not doing, actually, now that I think about it? Where's our parser? Puzzle input, puzzle input, puzzle input. We don't return the values. Right? We have values here. And now we have literals. Anyhow, good luck. Still try to solve part 2. Appreciate it. Like I said, I think we're almost done with part 1 here. Just working through the test cases. If the type ID is 4, then we have the literal inside of it. Okay, that's good. We need that. And we have a bunch of failing tests right now, so let's go fix those. We have test A, test B, test C that are all failing for whatever reason. Oh, they're all panicking now. That's why. Let's go back to our fold. Our fold is, this is a lot of code. We're doing if let here, else 0. So now we're only failing a couple of them. Test puzzle input and test operator 1. Test operator 1 now has to deal with having the actual literal in here. So this is, where's value 1? C. Test operator 1 parser, operator 1 parser. Has literal 1, literal 2, literal 3. Two, 3. Now we should have 2 failing. Puzzle input. The puzzle input also needs to have a literal 2021 packet in it. Test puzzle input, literal packet in here. Okay, so we're handling literals now. It's too bad this doesn't give us the expected output. Okay, so this represents an operator packet version 4, which contains an operator packet version 1, 5, 6. I think we identified that that is correct. So let's just force this to debug out as the only thing to debug out, and just check that we have a 4, a 6 and a 5 and a 1 and a 4 that contains a literal. 6 and a 5 and a 1 and a 4 which contains a literal value version 6. This is a bit of an inefficient representation. I don't know that I want to refactor it at the moment. If we look at literal and we look at what literal is giving us back, we are artificially constructing the packet literal, which can't have anything below it. So maybe we just return the U size here. Is that U size? We're doing U32 here. I'm going to do U size. And then literals here. This is not values. This is a U size that comes back. This is value. And this is now packet literal, which will take these two and give us the value, which is value. So we've cleaned up our representation a little bit. I'm going to go back to this and pull these two up here. And just modify our struct. And this is going to be value. And this will probably fail to compile because I did something somewhere. 110. Can I do this? Expected U32. So let's do U size here. 225. Yes. So these now have to contain that, but this is what we're going to do here. These return values. So those will be fine. This comes back up to here. And this is value. Do this. Value. And these are all literals. So now we've got a slightly different representation. 173 is going to be our fold. No, it's not going to be our fold. It's going to be this packet parser test. Okay, and now we've got test A, and test A fails because no matter which one we have, actually, we now want to fold with that. Let's do this. Bing bong. Okay, so can we do a multiple destructure? I don't think we can. No version on reference to packet? That's incorrect. Well, I guess technically that is accurate because it's the type and we haven't identified which type we have yet. That's disappointing, but we can do a match here instead since our logic has to be slightly different anyway. And this is going to be packet literal with the things and the stuffs, and this is going to be nothing, but this is going to be version type ID here. We aren't using the other thing. This is fold. This needs to come there with a comma. And now I'm just dealing with syntax errors that I've created by doing this. So match goes to here. This returns 0. This destructures a packet literal. This random packet is just sitting there. So match. Oh, what are we matching? We're matching packet. Duh. Okay, that was the issue. We aren't using this. We are using this. We aren't using that. We're returning the value itself, which is going to be the wrong type, is what's happening here. usize found u8. I'm going to return this value, basically copied into a usize. Okay, and now we're back to our problem. So operator, packets, operator, packets, operator, packets, literal. So 6514 for packet A, correct structure. Let's get rid of this panic. Let's open up B. So A should pass and we should panic to see B. One failed. And this is, what is this supposed to be? Operator packet version 3, which contains 2 subpackets. Each subpacket is an operator packet that contains 2 literals. So it is version 3 operator packet that contains 2 packets. So operator and literal. Why is literal version 0? Oh no, is that what I did? Okay, operator version 0, type ID 0, literal version 0, type ID 4, version 5, type ID 4 for the literal. This feels wrong. This feels like the wrong structure that we parsed out of this. We have an operator packet with a version and 2 subpackets. So we have an operator packet with a version of 3 and 2 subpackets. Correct. Each subpacket is an operator packet that contains 2 literal values. Each subpacket is an operator packet that contains 2 literal values. So this one and this one are the valid ones. And this one should be 1 level up, is what I'm getting from that. So why is that nested? That nesting is the problem. So part 1, we can debug binary as string, and we can do so to grab the binary output and check this ourselves. Right? So let's do this. 3, 3. So 11 is 3, 0 is 0. Operator packet of 3 with a type of 0. Type of 0 is the 11-bit version. It's a mode of 0, sorry, right? Well, let's find out. We do the operator. We get a 1. Mode 1. Mode 1 is take 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. At which point this turns into a number. That number is 2. So there are 2 subpackets that we need to start parsing now. So this is, label this correctly, packet. Packet. Subpacket 1. Which is another 3 and another 3, which is somewhat obviously 0 and 0. 0 again is the take 11. No, 0 is the take 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15, 1, 0, 1, 1 is B. B in hex converted to decimal is 10, 11. So these are, the subpackets are size, wait, no, that means we get mode 0. Sorry, mode 0 means take 15. We took 15. Why aren't we using this bits? Ooh, is that our problem? This is why you write tests. Input bits. So this should be input, but it was not the right input. Right? Bits. And now what we have here is operator literal. Okay, this is correct. This is the right way to do it. See, just work through the tests. Those pass. I bet you these pass too now that we've fixed that bug. Everything passes. We're ready to actually execute on part 1. So let's get our puzzle input and hope that there isn't an additional problem to solve. I don't want the debugger. How do I bring up the editor? E? There we go. Oh, what is this and how do I get rid of it? Input. This. For a run bin part 1. Hit stop. Okay. Is that running something? It's running the debugger or something, right? I don't know. I hit some hotkey and it did a thing. So that's the answer for part 1. So kind of an intense parser. We had to read a lot. We had to go through our tests a lot. But the whole process of identifying problems through iterating through tests is really, really, really useful when you're writing parsers like this. So should we go over this? Did y'all catch basically everything? I know we were a lot in the weeds there. So let's do, we have this packet enum, right? And we have a number of parsers. Let's close these up for a second so that I can pull them out. So process packet will close up to process part 1, right? We start here and we have to take the hex input and convert it into binary, which we do with hex as binary string, which uses the binary formatting of the number version of the hexadecimal number. That gives us 1s and 0s padded to 4 digits. Then we apply the puzzle input, which at this point really should be called packet, right? Puzzle input is not just the puzzle input that we have for other days. This is our packet parser. So I should name this packet and not puzzle input. Packet, the parser, takes 3 bits, converts it to a number, gets the version. Takes 3 bits, converts it to a number, gets the type ID. And then we match on that type ID. If it's number 4, we have literals. If it's anything else, we have something that we need to operate on in part 2, right? So what we've done here is we've converted our packet data structure, our struct, to our enum actually, to be either a literal or an operator. When it's a literal, we get a value. We still have the version and the type ID because we need to keep those around so that we can add them up later. And the operator also has the version and the type ID. The type ID for the literal is always going to be 4. The type ID for an operator can be anything really. And then we need to apply the operator parser, right? So the operator parser takes, the rest of the input. And if it's not a literal, then what we do here is we take the length type ID, which is either going to be a 0 character or a 1 character. Depending on whether it's 0 or 1, we do a slightly different thing. For the 0 case, we take another 15 bits and we turn that into a number. Do we turn that into a number? Yes. We take 15 bits and we turn those 15 bits into a number. We use that number to take that many bits, right? So we've got a 15-bit number that tells us how many bits to take that will contain the other subpackets. We take that many bits out, right, from the input, and then we apply a parser to the piece that we took out. So we take out the number of characters that represents all the subpackets, and now we apply the packet parser to the subpackets. So that will give us a vec of packets, basically, from that piece we took out. And then we return the packets with the full input, or with the input for the subpackets taken out. If it's a 1, we get that number from the 11 bits instead of the 15 bits. We use that number to calculate the number of subpackets that we are going to need to parse. And then we apply the packets parser that many times. So these can be variable length, but we still get back a vec of packets. All of that builds up into this packet structure where we either have an operator that has more packets or we have a literal. Because we have it that way, when we go to sum up all of the version numbers, we can just recursively go through this function, this process packet function, pull out the version, whether it's an operator or a literal, and then go through all of the packets that that packet contains if it's an operator and sum those up. Or we can just return the version if it's a literal, which means that we're at the end of the tree. One thing to note is that Derek mentioned that we could implement like sum for this in some way. And I believe that that's true. I believe we could do something like that. We chose not to. So now we're on part 2. And it only took us 3 hours. Long stream today. I knew it was going to be a long stream when I read like 15 paragraphs of little itty bitty, put this here, put that there. But that's kind of like, so what you saw today on stream was actually what it looks like to build up a parser. You get kind of like this spec. The spec raises more questions. You answer those questions in the implementation. You write tests to cover those cases so that you're aware that those are either passing or failing. And then you keep going and you go back to the spec and you're like, okay, it says it should do this. Does it do that? Doesn't seem to do that. Go back to the spec. Okay, maybe this other thing. And then we write a test for that. And it's like, so our implementation starts to diverge a little bit from the spec. But it's because we've made parsing decisions that are not encoded in the spec. Now that you have the structure of your transmission decoded, you can calculate the value of the expression it represents. Literal values, 4, represent a single number as described above. The remaining IDs are more interesting. 0 are sum packets. Their value is the sum of the values of their subpackets. If they only have a single subpacket, their value is the value of that subpacket, so we can sum the subpackets. 1 are product packets. 2 are minimum packets. 3 are maximum packets. 5 is greater than packets. If their value is 1, their value is 1 if the value of the first subpacket is greater than the value of the second subpacket. Otherwise, their value is 0. Less than packets, same thing, other direction. Equal to packets, same thing, but for equality. Oh, that hurts. Okay. No, we wrote this correctly, so this will be easy for us. Using these rules, you can now work out the value of the outermost packet for your bits transmission. These finds the sum of 1 and 2, resulting in 3. Yada, yada. I don't think I'm even going to write tests for this. Zero, 1, 2, 3, 5, 6, 7. So match packet. And then in here, we do match version. Is it match version or match type ID? Type ID. right? And match type ID does 0, 1, 2, 3, 4, not 4, 5, 6, 7. So these all have to have answers. Of course that didn't work. Why didn't I click the right character? There we go. Oh, we said we aren't using type ID. There we go. Does this need to be dereferenced or something? What is type ID? Is type ID even the right thing? Oh, right. And we panic if we have anything else because we can't have anything else. So 0 is sum, right? So sum is what we were doing before. Packets with type ID 1 are product packets. So can we just map here? To process packet? This is a show off of how good Rust is, basically. All of these have exactly 2 sub packets. So we'll do this, right? We map these. And then we do I think we can use assert equal like this, right? So we do this. So we're iterating over these, and this is what, less than? And this is equal. And none of these are let mute because I didn't say let mute. The other thing that I want to do is I think these have to be value. So if we run it on part 1, of course it doesn't give us the answer to part 1. Why would it give us the answer to the part 1 input? Really? Like, come on. Okay, so this is going to be the same thing. Any process packet. Oh, I just changed the entire thing for process packet, didn't I? Oh well. There's going to be process packet 2. This is going to be called process packet 2. This is going to be process packet, and process packet is going to take the version here. And all of these for process packet are going to go away because we only have the one, but we're going to change it to the sum and make sure it still works. Expected U32 found U size, process packet, part 2, is that the problem? $524 wasn't our answer for part 1, was it? It was $889. Cannot satisfy U size as add output equals U size. Type annotation is needed. So let's do this. $889. So this is the new and improved, amazing way of doing part 1. We can just do sum. We don't even need to impl anything. We just need to say we're returning the sum from the packet literal because the packet literal is the end of our recursion, and that pops back up into this, which then gives us the version for everything, and we sum it up. So what do you think? We just run part 2 and see if it works? Process part 2, process packet part 2. I didn't do the thing where I'm running it on the test input, did I? No. So process part 2. We don't take the versions, right? Yada, yada, yada. The sum of 1 and 2 resulting in 3. Maybe we just do these tests. I didn't want to do these tests. We can write the tests. It's fine. Just cleaning up the input so that we get the right test stuff. Produces 0, produces 0, produces 1. Okay, so now we have our inputs. Let's get rid of all these dots. And then we have to write basically the same thing we did for the puzzle input, right? Where's puzzle input? Packet parser tests, test puzzle input, test part 1. We didn't do a part 1 test, did we? Interesting. Why didn't we do that? All right, let's look at the input and the output here. Process part 2 takes the hex string and returns us the numbers. So it'll take these strings and return us the numbers, which is totally good. So let's do X. Nope. Nope. Yes. Let me do this first. Let me space that. Okay, kill. Nope. I do the wrong thing every single time. Okay, so we're going to write test. This is going to be fn test part 2. Do these inputs work as the identifiers? I think they do. Little sneaky trick there. And then this will be assert equals these numbers, comma, process part 2, this input. Right? Unclosed delimiter. Perfect. Just what I wanted to hear. I forgot to put the closing brace on every test. Did that work? All of the tests failed. Well, not all of them. This one succeeded. Assert equal 3. Process part 2, that. How did you do the thing where you pasted all the different inputs at the same time? If you have multiple cursors in VS Code, right? So you know how to do multiple cursors. You do this, and then I think on Mac it's Option and click, right? So I have a bunch of multiple cursors here. I can do that on selections as well, right? And then when I do that on selections and I hit Command X to cut, if I set it up such that I have the same number of cursors as are in the copied stuff, when I paste, it will paste all of those. So really all I'm doing is I'm storing that in the copy buffer, the cut paste buffer, whatever you want to call it. And then I'm just pasting them in because I have the same number of cursors. Okay, part 2, C200B. Let's start with that one. Actually, let's do this. Cargo test. There we go. So you can cargo test and just like throw in a word here and it'll run just that test. Okay, so left 3, right 8, because we're not adding the first value is what's going on here. Process part 2, 0, 1, whatever. Version. We don't use the version number, right? C200, 1 and 2, resulting in 3. So let's do this. Every time we hit literal, we'll debug the value. So when we hit literal, do we hit literal? I don't see any debugs here. Am I calling the wrong function? Process packet 2. Part 1, process packet. Part 2, process packet 2. Process part 2. Left 3, right 8. Process part 2 is the right thing. It is doing the process packet. We don't need to change the way we're interpreting it. We just need to go process packet 2. So debug, run the test again. Process packet 2. And we just immediately fail. You're calling process packet from all your nested process packet 2 matches. You are the winner for today, Derek. Thank you so much. The typos are the worst on stream. The typos are easily the worst problem to deal with. Because while you're holding one thing in your head, another thing goes wrong and like you don't catch it. Okay, so that all works. So we run bin 2. And we got a gold star. So thank you, Derek, for the typo mention, because I would have spent another half hour on that. Oh, dang it. Darn it. Okay, so everything works now, right? And really, the thing that I want to get across here is that let's move this over to here. Oh, this is the wrong one. Let's go. Where's my Chrome window? There's my Chrome window. Why did the Chrome window come over? Let's minimize that for now. Pull this over here. Come to 16. Okay, so in this fold here that we did, this kind of really shows off the power of Rust's iterators, right? So we've got a match packet here on the packet operator, and the packet operator is an enum that has either an operator or a literal value, right? So the literal value is the end of our recursion, which means that we just return the value. And the operator contains the integer, which controls what we do with those values. So the power of Rust's iterators, because we have packets which are a vec, is that we can iterate over them, and the first value is 0. It's sum, right? So packets with type ID are sum packets. Packets with type ID 1 are product ID 2 are minimum. We can just do the iterator, make sure that we have the values for all of the packets, the literals, by calling process packet. So we're recursing down, and then we just sum the values that we get back. And then we do product on the values that we get back for 1, or we min on the iterator for 2, or we max on the iterator for 3. And like doing this whole thing is, it really just shows off how nice Rust iterators can be when you're doing these sorts of things. And realistically, we could actually do this even further, right? We could do this. And reduce all of this code that we have in here. If I can breathe here. Packets.next. This does need to be mute as a result. Match packet. We open the brace here. We close the brace here. And this is gone. And this, provided I didn't mess up the immutability here. But, I don't even have my terminal anymore. Bring my terminal back. So we cargo test, everything still passes. And what we've done here is effectively converted the thing that were just talking about with the iterator into this, like we generate the iterator up here, and then we just say, we sum the packets, we product the packets, we min the packets, we max the packets. Like it becomes a very similar like read through, or a very simple read through, right? What are we doing to the packets? We're summing them. What are we doing to the packets? We're multiplying them, etc. So I don't know. I really like the iterators for stuff like this. I suppose it's time to run the dat heap before we finish. So let's do part 1 for dat. Next year, I'm going to have a tool to do this for me, to do all the benchmarking and stuff. So we've got 65K bytes for part 1, 65K bytes for part 2. Nothing changes. That shouldn't be a surprise. We aren't doing anything different other than the processing of the stuff we're doing. And the processing of the stuff that we're doing is not actually allocating anything differently either. And the runtimes are basically the same. I don't really consider this to be a difference. Right? Like when you start talking about the runtimes of these two things, like a nanosecond is not enough to make a difference. Not on a 350 nanosecond run. So we've got 340 and 342. Like 2 nanoseconds. That's the difference between the two runtimes. Not a big deal. So I don't know. Maybe we can optimize this a little bit. I think that I'm done for on stream. It's been a long stream today. Writing parsers is time consuming is the way that I'll put it. So it took quite a bit. So what you just built, that's kind of like an AST, right? Yes. Exactly. It is an AST, actually. So it's a structure that represents the structure of the thing that we're processing, which came in as hexadecimal, right? So we turned a string into a structure that we could then process. or execute, right? Depending on who you're talking to and what context you're talking in. Funny, but you keep messing up NS and US. US is microseconds. Oh, thank you. Thanks, Johnny. Yeah, I appreciate it. So this, one of those days. It's one of those days. So this is microseconds. This is running in 342 microseconds. Which is even better. Just one of those days, you know? But everything's done. I guess we're not really going to improve that runtime at all, are we? But this is very high level code for running in microseconds, you know? Like, is NS and US a 3 jump? Let's find out, because my brain isn't working and I'm going to tell you the wrong thing if I don't Google this. NS is nanoseconds, which is 10 to the 9. US is microseconds, 10 to the negative 6. So, yeah, exactly what Johnny said. Jesus, now I think, have I been doing that for every day? I bet you I've been messing that up every day. The next one is picoseconds. I don't know. I honestly don't know. Let's commit this day 16. Okay. So, brief overview of maybe anything else. I think the only thing that we do here that is of any size consequence is the allocation of the vex for the operators. Right? So we're doing many one here and stuff like that. For this version of it, we could say, hey, we have an array. For this version of it, I don't think we can. So yeah, I mean, there's a couple of things here, but nothing major. We can take a look at the dat heap before we leave. Let's do the dat heap for, I think we have part 2 up right now. So let me pull that. I don't have my browser up. Let's go for dat viewer. Load the dat heap. And we're talking, that's the wrong one. I loaded the wrong day. I do that every day too. I Rust, day 16, dat heap. So we're looking at 65 kilobytes. It looks like there's nothing else at the root. Let's see what the highest level things are. Oh, there's a couple of them. So this is many one. Many one allocates a vec. Totally makes sense. 9K. This is many mn. Many mn also allocates a vec. Many 0 also allocates a vec. That's 14K. This is, what is this top one? This is vec allocation for the string that we build up. Yeah, this is our strings. So this is converting the hex to the binary string, probably. Where's the identifier for this? This is in operator, it's in many mn. It's the literals, so the string construction and the literals. But yeah. All right, I'm gonna call it. I admit I haven't done this challenge today, but you started streaming my exact solution. Now I have to try it using the streaming API in the weekend. Yes. So one thing, I did it with, I think, in a way that won't be compatible with the streaming, right? So I do a dot length somewhere in here. So for literals, I do dot len. This is removable, but it requires having all of the input. So could calculate it in a different way. But this relies on having all of the input. But yeah, other than that, I think streaming this would just be a matter of doing this, right? The question that I have is mostly around how do we get this to actually be binary? Okay, yeah, so that gets incomplete. So a couple of changes need to be made for it to be streaming capable, which is as I expected because we did it complete to start with. Could just be move the count to be part of the parser output. Yeah, of course. I think that there are very like simple mechanical changes to make it be streaming capable. But the one thing that I'm actually interested in is, can we read this out as bits? And I actually don't know how to do that. So Johnny, if you end up doing, because right now we're doing hex as binary string, which is a function that just converts using format. And I know that nom has bits, right? So nom bits, right? So if there's a way to read this file in and then parse it as bits, that's probably going to have a different impact on runtime and stuff, I would assume. So if you do that, let me know, because I'm going to try to do that myself and I don't know how to do it. And if I get it, I'll talk about it on stream tomorrow or whenever. So that's going to be it for me. Thanks everyone for hanging out. This is super fun. This is 16 days in a row now. So we'll be back tomorrow for day 17. I'm going to go take a nap because I'm tired. Thanks everyone. Catch you.